Okay, hopefully I'm recording, sharing screen, everything else is working correctly. And okay, we have a slightly fewer than usual students, but that's fine. I'm not hurt at all. So today we'll be doing diffusion models. I'll be giving you guys diffusion models are getting super popular these days if you're doing image generation on all kinds of stuff. Like everyone has image generation these days, whether it's DALL-E or Midjourney or whatever. All of them use some version of what's called diffusion models. So today what I'll be doing is giving you guys kind of brief overview of how it works, a little bit of how the math behind diffusion models work, which I promise won't be too difficult. And then we'll be doing a lab. Essentially, I'll be programming a diffusion model in front of you, and you'll be able to see how it works. And I'll share the notebook with you. So later on, you'll be able to understand what's going on. Okay, so this somewhat complicated infrastructure that you see here, architecture that you see here, is called latent diffusion. It is a somewhat more advanced, somewhat more accurate version of a general diffusion model. This is what's used by Stable Diffusion or Midjourney, or a version of this is also used by DALL-E. All these common and popular image generation models. So today what I'll be doing is I'll be going through all these little boxes that you see here. First a pixel space, then I'll talk about what's happening in latent space, and then I'll talk about how the conditioning of the model is done. This is not, you don't have to go too deep into it unless you're a researcher working in this field. But again, understanding how these different parameters, how these different modules work, it'll be super useful, and you can do it on your own. If you have your own sketches or if you have your own pictures, you can put them into a diffusion model, and it'll give you really good results. That's how they're designed. Okay. So today the topics that we'll be talking about is, oh my God, I don't know what happened to the fonts. They're way too small. Let me see if I can share both the side displays as well. Okay, so if you're unable to read this, they're up on the side displays as well. So today we'll be talking about diffusion models, stable diffusion in particular, but in general diffusion models, some of the math behind denoising diffusion model, that's a DDPM paper, how we use UNet, a form of convolutional neural network within diffusion models, and how the whole text to image and image to image generation process works. But we'll be covering it in broad. So some of the things that will help if you know are some of the basics of probability and statistics, because a lot of the math behind diffusion models rely on knowing, say, Bayes' rule and like how Gaussians work, what's probability, what's likelihood, things like that. You don't have to know these in detail, but just understanding how these things are will help. And I'm not going to go into details of how convolution works, but it'll help if you know what's going on. So let's take an example. If you have never heard of Stable Diffusion or Midjourney or DALL-E, let's see an example of how they work, right? So this is an example of the kind of output that Stable Diffusion gives you, right? Stable Diffusion is text to image. It's not image to image. It's not sequence to sequence. It's not text to text. What it does is you give it a prompt of whatever random stuff you can think of, and it'll create an image that comes closest to that prompt. So in reverse, if you tell a convolutional neural network to classify this image, it'll give you something similar to this. So it's doing the classic image segmentation, image classification problem in reverse. So you give it a text, and it'll try to generate some image that comes closest to this, right? So this particular model was generated by Stable Diffusion. It's open source. It's available on that link, so you'll be able to use it. Originally, Stable Diffusion was trained on very low resolution images comparatively, like 512 by 512 images, and the text that the text that it recognizes was generated using something called the Lion 5 billion parameter dataset, right? And you can train Stable Diffusion, the model that generated this, probably not on your laptops because it requires at least 10 gigs of VRAM, and it probably requires an NVIDIA GPU unless you're a GPU expert. So again, it has 123 million parameters. So a scaled down version of this can run on your laptop, but preferably if you can get time on the UH HPCs, you'll be able to create your own Stable Diffusion and train it on your own images, and so on and so forth. So more examples of what Stable Diffusion looks like. So the prompts for all of these are something like an astronaut riding a horse, or a cat in the style of I don't know, Van Gogh, Edward Munch, something like that. Uh, Munch probably, yeah. And the final one, a girl dancing in, like, I don't know, impressionistic style. So those are the kinds of text, and this is the kind of image that generates. So what does it look like when it's doing this kind of image generation? Because what you see as an end user are just these images. But we are computer scientists here, right? We are trying to be computer scientists. So we need to understand how these images come to be. So as an example of what it looks like is, this is playing. So it's noise, and this noise is changing into an image. So this is what you'll be doing. This is what diffusion model does. It trains by doing the reverse, and then it generates by doing this. So all the images that you saw on the previous page were generated something similar to this. So this is like a ballerina in front of starry eyes, the Van Gogh. So again, so you can see that it's taking noise and it's generating images from them. So we've been talking about generating images, right? So one of the things we need to understand is what do we mean by image generation? So what is a generative model, right? So you guys have Mahin taught you guys about VAEs, right? Variational autoencoders. Those are a kind of generative models. There are also there are various kinds of models. There are GANs, generative adversarial networks. There are diffusion models. There are Hopfield networks. So there are lots of different kinds of neural network architectures that generate an image or generate data, essentially, generate some distribution. So what do we mean by a generative model? Okay, so a generative model in computer science terms or in statistical terms is a model that learns, given a data set, it learns the probability distribution of that data set, right? And then once it has learned how that data is distributed, whether it's in pixel space or whether it's in text space or any other kind of latent space, then we can sample from that distribution, like you do random sampling from a distribution, to create new instances of that data. So you take some data, you take a photo of a classroom like this, or you take a photo of a landscape, and the model tries to learn how pixels are represented in that image, right? So there's a distribution of that image. And then if there are similar things in those images, so if you take pictures of cats and dogs and you create your diffusion model by training them on cats and dogs, then the model doesn't know what cats and dogs are. So what it does is it creates a latent space where it associates things that look similar to each other in that high dimensional latent space. And then when you use that model to recreate something, you get images of cats that were not in the original training data set, because your random sampling doesn't give you the exact whatever you have trained on. So that's kind of a generative model. So like I said, there are various kinds of generative models. So the top three, those are not what we're going to be talking today. Those are GANs, VAs, and flow-based models. So GANs are generative adversarial networks, VAs are variational autoencoders, and flow-based models. So they've been GANs, VAs, flow-based models. They've all been successful. Like they generate very high quality images, and some of those are used in diffusion models as well. But each of them have limitations, right? So GAN models have the problem with GAN models is that their training process can be unstable. I'll talk about what happens, what mode collapse in GAN models are. I'll talk about it a little bit later. And due to this adversarial uh, architecture of a GAN, they have generated images can be less diverse. It creates problems of their own, right? VAs relies on something called surrogate losses, which is again not very well defined, and it creates problems in image generation. And flow models, which are actually, if you can implement a perfect flow model, it'll be the best performing of the bunch. But getting a perfect flow model where whatever distribution you have, you're able to exactly accurately recreate that distribution, that perfect reversal, that is a very challenging task, and that's a in general that's an NP complete problem. So nobody has solved this problem. So we approximate it, and so because it's an approximation, it's not as good. So diffusion models, what they do is they create a Markov chain. So they create a Markov chain of diffusion steps to slowly, incrementally add random noise to that input image. And then we use a neural network to learn how to reverse that process. So I'll go into more detail. But first, all of these we're talking about, we are recreating the original distribution of data, right? So why do we model this data as distributions rather than as anything else? So pretend you're a criminal. Even if you are, just pretend for now. So if you're a criminal and you want to generate fake people, right, for advertising purposes, for, I don't know, for taking over a country or whatever, for each of those fake profiles that you're creating using that you as a criminal need, all of those fake profiles need some characteristics, right? They need to be of some certain age. Their distribution of gender has to match the real world. They have to have of a certain height. So how do you do this? So you ask the U.S. Census Department or whatever statistics department of the government for these statistics, right? This age distribution and height distribution and whatever. They're usually a Gaussian distribution, right? So initially what you might end up doing is you just sample like independently from each of these distributions, right? So you take a random age and you take a random height, and that's how you create a profile, right? But that would not be that is a pretty high probability of giving you completely wrong stuff. So you can have someone of like 1.9 meters in height, but 2 years in age, right? So the world's youngest basketball player. So these independently sampling from distributions like this causes unrealistic problems, like problems that won't come up when you're doing math, but problems that would come up when you're looking at the outputs as a real human being, right? So to generate data that makes sense, you need to do joint distribution. So all these different parameters, all of them have to be like, you have to consider them together. So the probability of someone being age 1 and height less than half a meter is high, but someone being age 1 and height 1.5 meters is very low. So these kinds of joint probabilities have to be considered. And so we do conditional probability, and then we end up marginalizing certain variables and things like that. So to understand, this is why, like, to get actual real world data, we need to model the original incoming raw data as distributions, because otherwise it's very difficult to get like realistic data from all of them. So what does it look like? So your training and testing sets. So you can see that it's a bimodal distribution, right? So the goal of any kind of generative model, whether it's GAN, VAE, flow, or diffusion, which is what we'll talk about today, is to create a model that recognizes this distribution. And then when you sample from this distribution, whatever you get, whatever is output of those models, is indistinguishable from the original data. Right? So that's it. So now there are two broad ways of learning this distribution of data. Right. So first, using log likelihood. So essentially, we sample from the distribution, and if the log likelihood of that distribution of that sample is very high, then that means it probably came from the training distribution. And if it's low, then it probably did not come from the training distribution. So in our previous example, a 2 meter tall baby would have low likelihood. And I don't know, a half meter tall baby would have a medium to high likelihood, like that. And the other way is using divergence metrics. So there are various kinds of divergence metrics. There's Kullback-Leibler divergence, there's elbow, lots of different divergence metrics. But what a divergence metric does is that it minimizes the difference between the training data, like it minimizes the difference between the training data and the distribution that the model has actually learned, right? So that's what divergence metrics do. And we end up using divergence metrics for stable diffusion as well. So before we get into diffusion models, like let's start with GANs, right? So what do GANs do? GANs take they take latent noise vectors, and then they distribute, they supply it to their generator after that generator has already passed through the discriminator, and then it creates it creates this X prime, right? And then this X prime is sent to the discriminator, which tells whether yes or no, whether whatever the generator has created is it a valid thing. So that's how generative adversarial network. So this is the generator and this is the adversary. And the adversary, every time the generator creates something, it goes to the adversary, and the adversary tries to guess whether what it has created comes from the original distribution or not. So there are lots of problems with GANs, which is why they have kind of fallen out of favor in favor of diffusion models these days. But the biggest problem is that vanishing gradients, right? So if this discriminator is training faster than your generator, then your discriminator will never allow anything that the generator creates, right? So if this becomes too powerful compared to the generator, then anything that the generator creates, the discriminator will know that it's not part of the original data set, and so it's going to fail it, right? Which is a challenge to balance, especially if your GANs are have billions and billions of parameters, right? And the other challenge is, which is something that if you create a GAN on your own, you will definitely deal with. It's called mode collapse. So what happens is that the generator finds a local minima or a local maxima, whatever. It finds an extreme position in the distribution that is probably not the global optimal solution, but it creates this exceptionally plausible output, whatever this generator is creating, and then it will continue generating because there's no heat, there's no temperature control that makes the generator create something else. So what happens is the generator creates some extremely plausible output, and then the discriminator learns that plausible output is either yes or no, doesn't matter. It might learn to reject it. And then the generator will continue, whether it's accepting or rejecting, the generator will continue recreating that particular image or that particular distribution over and over and over again. And the discriminator will keep rejecting it. And so it creates a loop, right? And this is called mode collapse. And this is very hard to deal with, right? So in order to deal with this one-step problem where you give a latent noise vector and then your generator takes it and tries to create a distribution from it, this one-step problem, trying to solve this one-step problem, people came up with something called denoising diffusion models, DDPMs. So this is how diffusion models work, right? So you give it a noisy image like this, and then step by step from that noisy image, it recreates the original image. How does it do that? It tries to estimate a reversal function. That is Q, where xt is the currently generated image. Xt minus 1 is the image generated one step before. So Q of xt minus 1 given Q of xt, this is what we are trying to recreate. So that's the purpose of a diffusion model, but we don't know that. So we estimate it. What we do know is this. We know Q of xt given xt minus 1. Because all this does is it takes this image and it just adds noise on top of it. Right. So our function, it's very easy to calculate. You take noise, you take image plus noise. That's this. That's Q of xt given xt minus 1. This we know. But this reverse process where Q of xt minus 1 given xt, that we don't know in this Markov chain. So we try to approximate it using this P of theta, where this P function is parameterized by this theta parameter. So, and that in a real diffusion model is usually a unit or some version of a unit. But there are other possible models, right? So yeah, so what diffusion models do is it converts a simple base distribution like a Gaussian noise to the target iteratively. So go step by step by step by step via Markov chain, where the probability associated with the sequence of events is occurring based on the state in the previous event. So if this is valid, then it's a Markov chain. So if we know xt given xt minus 1, then that's a Markov chain. So if you have any questions, if you're having trouble understanding what I'm talking about, can ask me now. Okay. So let's do a small review, and this is something that I might probably end up giving you in your exams because it's a very easy question. So fundamentally, what's the difference between GANs and diffusion models? So GANs are one-shot generation, right? There you saw the generator, right? There's only one step in this generation process, so which makes it super fast, right? Because the model itself is fairly small. Diffusion models, on the other hand, are multi-iteration generations. Right? So you saw the Markov chain. It takes step by step by step. So this image generation process is comparatively fairly slow. However, the problem with this one-shot generation is that it's kind of hard to control, right? Because you have just one step, then you have no way of iteratively controlling what the output is, other than the discriminator. So if you are trying to train the model to move in a particular direction, it's very difficult to do. But in diffusion, because it's step by step by step, because it's a Markov chain, you can add in parameters, you can add in controls, you can add in constraints within those steps. So it's much easier to control during this generation process. And finally, because of this min-max way how adversarial generative adversarial network works, they're very prone to mode collapse. But in diffusion models, there's nothing called adversary, right? So the objective of a diffusion model is fairly simple, which makes it fairly easy to understand. So before we get into the math of how diffusion models work, this is an overview of how a diffusion model works, right? So this is in reverse of that image that you saw before. This is an image of a person, and you can see at x0, the image is like complete. And then as you move step by step from x0 to z1 to z2 to z3, you keep adding noise to it. And then at the end, at z of t, it converges to pure Gaussian noise, right? And this forward process is completely fixed, right? Because it's a standard process. You take an image, you add noise to it. But this reverse process, where you have this noise and then you try to generate the original image from it, that's where the complexity of a diffusion model comes in. And that's what we're going to talk about next. There's a bit of math in it, so don't be scared. I asked my Discord client for the single worst image they could think of with Be Not Afraid, and this is what they created. So don't worry about the math if you don't get the math fully. So we are talking about a general diffusion model, not any particular specific latent diffusion, stable diffusion, DDPM, or whatever. So for the forward diffusion process, there's a function f of x of t that we are trying to that we know of, and there's a noise g of t, right? That's fixed. But for that fixed process, for a diffusion model to work, there's a backward diffusion process that reverses the time domain. So it goes from t equals infinity to t equals 1. So for that purpose, we are trying this time dependent score function is what we are trying to estimate. This gradient of log p given x and t. So this is the backward diffusion process that we are trying to estimate. So if this function is stable and solvable, then we can reverse the diffusion process. And to create a stable and solvable time-dependent score function, that's why you use Gaussian noise, right? So if we can learn this, if we can learn that score model that we talk about, which we can approximate as log p of x and t, that means we are able to, if we are able to learn this, if it is at all learnable, that then means we can denoise the samples because we can run the reverse diffusion process where we can given xt we can recreate xt minus 1. And this score model is generally speaking a time-dependent vector field over over this X space, chi space, but it's not always time dependent vector fields, because as we'll talk about later, there are certain models of diffusion called clip models that that keep it time dependent, but also adds in more dependency, right? So the objective of training a diffusion model is to infer what is noise from the sample and then minimize that noise, right? So you're trying to, this epsilon is a Gaussian noise, and we're trying to minimize that Gaussian noise from that sample. If we have to have some control over what we are minimizing, because if we are unable to like do some form of conditional denoising, then we have no control over what's being generated, right? It's going to generate the same thing every single time. So for that purpose, we have some forms of conditional denoising based on some condition y that can be controlled, whether it's text labels, whether it's weights given, whether it's like weights in the training sample, and there can be many different kinds of conditions for conditional denoising, but it has to be added, right? In general, for this image-to-image mapping, that is taking an image of a noise and then recreating that actual sample of the original data, UNet is the most popular example. And we condition UNet using text prompts, so like clips that I'll talk about later. So this is your score vector field. This is what it looks like. And then when the reverse diffusion process is working, this is what it does. Right? It is constantly being guided by this by the direction of the score vector field, because it's a vector field. There's directions, and each and every one of those samples have been guided and taken to the minimals, and that's how we are trying to solve it. So next, this was a general overview of diffusion models. Let's look at one specific example of a diffusion model called DDPM, denoising diffusion probabilistic model. This looks complicated. You don't have to know all of this, but what I want to point out is that this is a forward process. There's a reparameterization trick that I'll talk about later, and that's the reverse process. So what the forward process does is that for x from 1 to infinity, conditioned on knowing the original image, x naught is like whatever image you're adding noise to, and so we are cumulatively multiplying it with noise. So this is the Gaussian distribution with mean and variance. You can see here, and using this mean and variance, we are at every step we are cumulatively multiplying the noise to the original data, and that's how we are coming to it. Now, one advantage of this is that you see this red thing I've marked. This is called the reparameterization trick, because well, in general, you can do some math, some Bayes theorem math, to prove that as t over there approaches infinity, you eventually end up with like an isotropic Gaussian, right? But because this forward process is fixed, because like this cumulative multiplying is fixed, you don't have to actually do this multiplication. Because if you have like 10,000 steps and you're doing this every single time for every single image, that's not needed. So you can do this reparameterization to get the current image at any time t using just this formula. Now, how this comes out, you can look at the paper. I've linked the paper in the description. But so you don't have to do all the steps. All you need to, if you want to know the out of 10,000 steps, you can just stop at 5,000 and 10,000. And using that formula, you can do it. Right? And I talked about divergences. This is the one divergence negative log likelihood that you're using. This is called elbow evidence lower bound. And the forward process is, like I said, we are trying to estimate t of theta, where we are trying to find out xt minus 1 given xt, right? And that is done by UNet. So how does this work? There are two steps. First is training, where we take a sample q of x naught. We create a random number. I'll show you how I'll go this whole process. I'll do it during the lab so that you can understand what's going on. We sample from that noise, and then we do the reparameterization trick to add noise to that sample. And for the reverse process, we, instead of sampling from the original data, we sample from some noise, and then we keep denoising the image over and over and over again using this using this epsilon theta. Gaussian noise parameterized by some parameter theta. We keep removing this noise over and over again until we come to an actual image. So now that we know how the structure works, let's talk about how we actually generate this this new image using UNet, right? So this this code function that that I showed off earlier, we use UNet for this. So remember that image from the first slide. So we are talking about this part, talking about how UNet does this, right? So before we get into UNet, it's good to understand convolutional neural networks, right? So this is a very classic example of a CNN. This is VGG16. VGG stands for Visual Geometry Group. Yeah, that's what it stands for. So Visual Geometry Groups is 16 because there are 16 convolutional layers if you count. And CNN parameterizes an input function over these images. These features, whatever features a CNN recreates, are invariant to any kind of translation. So you can rotate the image, you can do any other kind of translational on the images. The features that a CNN learns remains invariant. And one good thing about CNNs is that it learns these features at various dimensions, right? So you can see it learns at 224 by 224 all the way down to like 14 by 14, right? So at various different levels of abstraction, CNN is very good at coming up with something good, right? So this VGG16 was created by Zimmerman and Simoyan from University of Oxford, and it's still being used. So it's still pretty powerful. So this is what a UNet looks like. So what a UNet is this is a CNN, and this is an inverted CNN. So you combine two CNNs together, one for the full downsampling system and the other for the upsampling system, and you get UNet. UNet was originally created for medical image segmentation, which it does really good at. Even today, even in 2024, UNet is close to state of the art for medical image segmentation, and a lot of people still use it. So if you're interested in medical image segmentation, knowing some form of UNet is like essential. Right? So this is how, like I said, the left part is CNNs and the right part is an inverted CNN. So you do this whole thing, you get a UNet. So how does this work? The downsampling part has a convolution neural net. It does some batch normalization, then it does pooling, and then here it says it's using ReLU, rectified linear unit. But in stable diffusion, in practical real world terms, people use something called GELU, GEL, which is somewhat more powerful, somewhat better results. So, and for the upsampling part, it uses convolution neural networks to upsample, and then it uses a softmax activation function. So to create this entire UNet architecture that you see here. The example image that you see here is satellite image segmentation for remote sensing purposes. Now UNet has some problems, right? UNet isn't the final, isn't the perfect solution for anything. So what is the biggest problem is that it is very, very computationally expensive because of how many steps there are, the downsampling step, the upsampling step, all of these are super computationally expensive. Now, this is fine if you're running it in a medical context where you have powerful computers which have already built the models for you, and all you need to do is send in medical images to it just to run it. But the training and if your input data is very different from what it has trained on, it is incredibly slow. In your assignment and in the demo that I'll show you today, I've created the most basic UNet possible, and even then it'll struggle to run like even once on your laptops. How do we solve this? So there are essentially two good methods to solve this. First is wait, did they both come up together? Whatever. So the first is you generate very low resolution images and then you upsample it externally, right? So your entire computational strength goes into one of these steps instead of both, right? So you save some time, but but this is still fairly slow. But the more common and more popular approach to solving the UNet problem is generate your images in latent space. Right. That's what's used by Stable Diffusion, DALI, Midjourney. Everyone uses this. So all your images are stored in latent space and they're generated from latent space. Um, I've been talking about latent spaces a lot. So if you don't know what latent spaces are, let me tell you. So latent spaces are kind of abstract, multidimensional space, right? Where all the feature values that we can't directly interpret are kind of stored. So this is where the latent space is there. So what it does is it encodes like the internal representation of whatever data you're training it encodes them in a meaningful way, right? As compared to external observation. So an example of this is for example, word embeddings, where you embed words, sentences into latent spaces. So some words have meanings closer to each other, right? How do you represent that? We know it. We know two words are close to each other, right? Whether they're like parts of speech or whether like two colors are close to each other or chair and table is close to each other. So there are various forms of meaning. There are various ways two words can be close to each other and two words can be far from each other. That the way that is represented in the backend for any model is called latent space. So we've talked about image generation, but we haven't talked about how do we guide this image. Right? So like if we are given a noise, it generates something, but how do we tell the model what exactly we want to generate? So say, for example, we take these perfectly normal images of two cats and two dogs. We train a model on these four images. And then if we start from random noise, what does the model generate? Right. We don't know what it's generating, right? So that's to do that, to know how like where we are trying to direct this Markov chain towards, starting from like complete blank noise, is called conditioning. So there are like I said here, there are three types of conditioning. What we'll be talking about today is explicit conditioning, but classifier guidance and classifier free guidance is also it's also in the presentation. So if you're interested, you can look at it later. So what explicit uh, guiding does is what we'll be talking about next. Is it trains using an image to text data set. Like for example, for Stable Diffusion, it uses Lion 5 billion parameter data set. So it uses text to label all images. Classifier guidance and classifier free guidance. So in classifier guidance, we know the diffusion model goes from noise to real image, right? So what classifier guidance does is it perturbs this trajectory of the denoising using by manipulating the gradients of the classifier, right? And what it ends up doing is you need to fine tune the classifier on the noisy images as you're training it up. It's complicated and it's not very good. In classifier free guidance, uh, it does the same thing, but it doesn't rely on you explicitly training it. So the diffusion model itself tries to get perturbations. So how do we get diffusion models to understand these text prompts, right? So the answer to that is what's called language multimodal transforms, CLIP. This is the final part of that image that I showed you in the very first slide. This is the conditioning, where we semantically map text to images, and we use that to recreate images using a diffusion model. So next up, just a very small overview into language modeling. Mahin is going to teach you how LLMs work in a couple of weeks. So for now, this is just like a very brief primer into language modeling. So what language modeling does is it considers words in a sentence as vectors. It's very basic. That's 101. So unlike in an image, Like the characters, the individual characters of a sentence don't contain meaning, right? In some languages, in some other languages like Chinese or Japanese, where kanji, like the ideograms have stand for certain meanings. So their word embeddings work very differently compared to like the Latin languages, right? So this is a word in a sentence. You semantically separate it. You love cats and dogs. The words that you're interested in are cats and dogs because that's what you want to generate. These words can be represented as indexes in a dictionary, right? But the problem is those even if you represent them as indices in a dictionary, those indices are meaningless. Like if you in a dictionary, what is the position of a word in a dictionary contains no meaning at all. Like if you're trying to recreate something or if you're trying to create an image, that is not relevant, right? So these are the token indices. Those have no relevance at all. So what do? We represent these words in a vector space, right? Try to represent these words in a vector space. So where the geometry of the vectors contains some meaning. Right? It's kind of it's easier on the screens to tell the color differences, but you can see cats and dogs are red because that is what we're interested in. The punctuations and the whatever that's called in English, those are less relevant. So those are colored differently. I works completely different compared to cats and dogs, and love is an adverb, so which is again coded differently. So this is how you initially encode it, right? And then we are not talking about attention and transformers and all the language modeling stuff. So just to know that meaning of like how word vectors work using RNNs or transformers is that they meanings of those individual words that you saw here are dependent on context, right? And the context is not always the same. What's a good example of this, right? I book a ticket to buy that book. Both of those words like are embedded completely equally. Like if you directly embed them without thinking about anything else, but they have completely different meaning in context in sentences. So word vectors should always depend on context. And what transformers do is it absorbs influence from like other words that are next to it or close to it in some semantic space to contextualize these words, right? So this is how transformers work. So initially, cats and dogs are red. You can see it comes to a transformer block, and then colors are the words that are closest to each other. It diffuses next to each other, and that's how it keeps working. So it keeps doing this over and over again. So every word knows what it means, what the meaning of that word is in context to other words that are around it, and this keeps going on and on and on. This is what a real world transformer looks like. So there are multiple things going on here. There are normalizations, self-attention networks, etc., fast Fourier normalizations, but you don't have to worry about that. But this is how transformers work. Now, going back to our diffusion models, what do we need this language modeling stuff for? So what this does is that some kind of language modeling. So this is an example of something called contrasting language image pre-training or CLIP. It's available it was created by OpenAI. The paper is Radford et al. Paper is available. So what it takes is it takes something like that text, Pepper the Aussie pup, and then it uses some kind of transformer to semantically separate each of the words in that sentence, and then it combines it with an image of that is labeled with that like an image that is labeled with that text. So it encodes that image, it separates it using some transformer, and then you see I1 T1, I2 T2, I3 T3. This is how the parameters mix together. This is the parameters of most relevance, right? So this is how it knows this using this clip, using this structure, that when you say pepper the Aussie pup, which part of it means what? Like pepper is a name that is not relevant to anything here, but an Aussie pup is more relevant to what you see. So that's how clip works essentially. So it learns a joint encoding space for both of them, for the text caption and for the text image. Hang on, I forgot about this. Attendance. So what this does is it maximizes whatever is similar between that text and this image, and like between the text between the image and its caption, and it minimizes everything else, right? And so now we know all the parts of that initial image that we talked about earlier. Let me see if I can open that. So this is the paper that we talked, where latent diffusion is created. And so for this image, this whole structure, now we have talked about all of them. We talked about how we take a distribution and we add noise to it. That's how it works in pixel space, and recreate that image from the noise itself. We talked about how the latent space and the UNet is recreated. That's this green blocks right there. And finally, we talked about clip and how that's done over here. Okay, so next up, what we'll do is I'll run a demo, right? So there's a bunch of slides in here that you can, if you're interested in, you can look at. I'm not going to talk about it here because it can get slightly complicated. And essentially we don't have time. So next up, we're going to move to, wait, hang on. Said all those things, but this was in the wrong thing. So next up, we're going to do a little demo. And this is an example of your homework assignment, right? So there's a car, very, very low resolution car from the Stanford cars data set. Then we keep adding noise to it until the image is completely destroyed. There's no information in there at all. Then we train a UNet on this process. And then from that image, if we go further enough and I don't know, if you squint your eyes and look at it from the side, there's a car there. So this is something I've like shrunk down the UNet and the diffusion model enough that it should be able to run on your laptop. If it doesn't run, let me know. Just run one step. Just run one step of the process, and that's perfectly good enough for me. Okay, so next up, what we are going to do is we are going to wait. How do I double the screen instead of? Oops. Screen. Okay, let me stop sharing. Give me a sec. Technical difficulties. Okay, this is working. This is working. Start menu isn't working. Oh no. Okay, fine. Okay. Well, this is going to be kind of hard to work on, but okay. Let me try regardless of what's going on. So instead of this, we want to do this. So this is what we are going to be doing. Okay, we are going to create this this mean and standard deviation, mean and variance in from the noisy data. We're going to add that mean and variance to the original data, and then we're going to try to recreate it. That's what we are going to do. Let me see if I can. This is so annoying. Very hard for me to type here and look here. Okay. We can't do it. So first, what we need to do is get the mean and standard deviation from that reparameterization trick that I talked about, right? Oh my God, this is going to be almost impossible. Okay. Okay, so the first thing we are doing is so from that original formula, let me open it here so that I don't have to do the whole thing again. So we need to know the mean. The mean, as we saw, was square root of alpha hat plus x0. Yes, square root of alpha hat times x0, and then square root of 1 minus alpha hat times noise. So that's what we're trying to do. So square root of alpha hat sqrt alpha hat times x0. This is what we're trying to do. And the other thing is the variance is square root of 1 minus alpha hat times some random noise. So this is what we are trying to do. Okay. So is it working? Okay. So first thing, what do we need? We need torch. Is it doing anything? Oh God. Okay. Import torch. Once we have imported torch, let's run it. Working. Okay, it worked. So first thing what we need is X. Oh, it was oh God. I'm so sorry. Okay. Let's select the Python environment. 10.2. So this was what was creating the problem. This is the slowest torch input I've ever seen. Let me zoom in slightly so that people can actually read. Is this readable now? Yeah, way better on the TVs. I have no idea why this is why I'm unable to duplicate my screen. Does anyone know a shortcut for Windows screen duplication? Thought it was something like WinD plus something else. Whatever. Too late now. So we don't have enough time for all of this. So x naught equals we're trying to create a random image with two batches, three channels, red, green, and blue, and let's say 32 by 32. So it should be torch dot and this is so weird to type. That's two batches, three channels, 32 by 32. Okay. We also need to create the schedule, the time schedule. That's the betas. So the betas would be let's say some linear schedule like torch dot tensor. Oops. Uh, I don't know, from some value from 0 to 0.25. So let's say 0.05, comma 0.1, comma 0.15, comma 0.2, comma 0.25. Let's say it's something like that. And then finally, the time steps that we need to see what's going on. Right. So t equals again torch dot tensor. Let's say 0, 1, 1, and 3. That's in the middle. So 1, comma 3, right? Oops, that bracket is in the wrong spot. Okay. Okay, so we have created all the preliminaries. So now that we've created this, we need to create what we saw as alpha x hat or alpha hat of t. So betas, the scheduled betas, that's the amount of noise that's being applied at every time step of the diffusion process, and the alphas are 1 minus betas. So that's how we create alpha hat, right? Remember the cumulative. Right, go ahead. I'm sorry. Oh, this 1 and 3. Oh, so 2 is 2 batches, 3 is 3 channels, and 32 by 32 is the size of the random image that we generate. Right. Yeah. I mean, this is not a real image, right? This is just random. So that's why it's That's why I chose this, and it's easy to train. Okay, so okay, now we know the alphas, we know the betas, so the alphas are very exactly 1 minus betas. I'm used to typing on a mechanical keyboard, so this typing on a laptop is kind of annoying. And alpha hat that we saw on this over there, alpha hat that we saw is a cumulative product, right? So alpha hat was defined. So these are cumulative products, right? This product symbol. So that's what we are trying to recreate. So if you have alpha minus beta, so next up we do the cumulative product. Thankfully in TensorFlow we don't have to worry about uh, doing it manually. Torch has a cumulative product of alphas. Axis is 0th axis. Yeah, the axis equals 0. Okay, that should be it. Right. Let's just see what alpha hat looks like. Yeah. So what this did is it took our betas, 1 minus betas, and then it cumulatively multiplied all of them. Right. Just to be sure, let me show you what alpha looks like. Alphas look like. Yeah. So the alphas were 1 minus betas. So they're 0.95, 0.9, 0.85, 0.8, 0.75. And then you cumulatively multiply all of them, and that's how you get alpha hat. Next up, we chose t as 1 and 3. Those are the values that we're interested in. So to do that, what we need to do is we need to gather. So alpha hat. Let's call it qt. Let's call it result, just to waste less time. So we do alpha underscore hat dot gather. We do it on the -1 comma t, and we need to reshape it because right now, if we gather it, it's just like 1 by 1. The shape is wrong, but for our actual images are 4-dimensional, right? They have the batches, they have the channels, and they have height and width. So we need to reshape it to 4 dimensions. So we have to do -1, 1 comma 1 comma oops 1 1, and yeah, that's it. Oops. Ah, brackets. Wow, first time. Okay, it worked. So next up, so now we have everything, right? So now we have the results, we have the key. Now all we need to do is create the noise value. So we need to create a noise vector that we are going to add to our image. So the way that's done is torch.randn, like that is in the similar structure as our original image, which is x0. That we have created the noise. Next, we create the mean. The mean, as you remember from this image, is right over there. Need to create the mean and the variance. Square root of alpha hat times x0. That's the mean. So mean equals what did we call it again? Result. Result dot sqrt times x0, and the variance is 1 minus. So it should be torch dot sqrt in bracket 1 minus what did we call it? Result? Yes. Times noise. Okay. And then x at time step, and then x at time step t is equal to just mean plus variance. And that's pretty much it. That's That's forward diffusion. So what does it look like in practice? Because this was just coding. So to do that, let's just take what we just did and put it into a function called forward diffusion. Give me a minute. We need x naught, we need t, we need betas. Betas in general are instead of just putting it on, let's just use a linear space. Torch dot lin space is 0.0, comma 1.0, comma how many did we need? We need 5. 5 is good enough. So we are creating a function, right? Creating a forward diffusion function, doing everything that we just talked about. So what we need to do is noise. So noise was torch dot ran n like x naught. Then alphas equals to 1 minus betas. Then alpha hat equals torch dot cumulative product. Alpha is, oh my god. Sorry, this would have been so much faster if I could just see what I was typing. Alphas x is 0. Then alpha hat e is alpha hat dot together minus 1 comma t. Then we reshape it to minus 1 comma 1 comma 1 comma 1. So I'm just doing what we just did into and putting it into a function. So this is alpha at t dot sqrt times x new. That should be alpha t is 0 and the variance is torch dot sqrt 1 minus alpha at t times noise. And then, oh, that's wrong. And then we return mean plus variance, comma plus. Okay. Okay, hopefully that worked. So now let's get an image of a cougar. Actually, you're looking behind the curtain here because I already did everything before doing it here. So this is an image of a cougar that we are going to just paste it here so that I don't spend half an hour. Okay. Shift tab. Let's hope it works. Oops, I need to import URL lib. What? Import everything. Okay. We took an image of a mountain lion. That image was, yeah, that image came through. So let's make sure that that image works. Image equals image dot open file. Yeah. Did I not import image? Oops. Yeah. Yeah, I'll import What's it called? Okay, that's a picture of a cougar mountain lion. And so once we have this, let's apply our diffusion process on this. But before we do that, we need to transform that image because this is a JPEG image, and a torch tensor requires something else. Compose. We need to change it from like an actual JPEG image. We need to change it to a tensor. So first, it's way too big to train. So let's do transforms dot resize to 32 by 32. Once we have resized it, we need to change it to a tensor. Dot to tensor. And then another thing you need to think about is that our noise is lies from -1 to 1, but our images don't. Our images are from 0 to 1. Right. So once we have changed this to a transfer, so what we need to do is we need to squish the distribution so that it goes from 0 to 1 to -1 to 1. And the way we do that is by applying something called a lambda. So we use a lambda to lambda t. What this does is multiplies it by 2 and subtracts 1. So what this means is that if in the original image, if something was 0, 0 times 2 is 0, minus 1 means it shifted to 1. And if it was at 1, 1 times 2 is 2, minus 1 is 1. So it remains at 1. So what it does is it takes a distribution and squishes it so that it fits our noise distribution, which is -1 to 1. I think that's it. I think we don't need to. Let's do the reverse as well. This form essentially does the whole thing, but in reverse. Oops, thank you. Oh my God, yes, you're right. Thank you so much. Okay, transform start compose. So, okay, so we're doing the reverse of everything. So transform start lambda. So this time what we do is lambda t is t, let me think, t plus 1 divided by 2. So we're doing the exact reverse of what we did last time. So t plus 1 by 2. Okay, there's another thing we need to do that if you have worked on image transforms, you probably know about. That is the color space, the color space, the dimensions in a tensor is different from the dimensions in a JPEG image, right? So we need to change the batch information from first to last, essentially. You don't need to worry about it. This is just something you have to do if you're doing this kind of image transformation. So we go from 1 to 2 to 0. Oops. Don't worry about what I'm doing here too much, but this has to be done every time, unfortunately. Wait, what? And then we need to transform everything back from 0 to 1 to the image color space, which is 0 to 255. So it's transforms dot lambda, where we do a lambda t, and we multiply the t with 255 dot. And then finally, we need to convert everything back to uint. PyTorch. It has to be uint 8. So it's a uint 8. I think we find hopefully there has been no typos anywhere. And then finally back to image. But did it or did it? Oh, I forgot the brackets in resize. Oops. It should be within brackets. Yeah. Oops. Okay, it worked. So let's add some code blocks here so that we can see what's going on. So now that we have done this reverse transform, whatever, so let's look at what it looks like, right? So let's do torch image is transform image. What did I call it? Reverse transform and transform. Oh my God. Right. Okay, it worked. All right. Something's working at least. And then we do plt dot im show reverse transform of torch image. And this is the image of a cougar, somewhat pixelated image of a cougar. And this now finally we do diffusion, and that's where we are going to stop. So we take a torch.tensor of 4 steps, 5 steps. So it's 0, 1, 2, should be in brackets. 0, 1, 2, 3, 4. And close. We create 5 batches because we need 5 images. So torch.stack. We take the image of torch image, multiply it by 5. And then we get the noisy images and the noise itself from the forward diffusion process that we created, where X naught is the batch image and T is time T. Okay. Oops, that was I made a mistake very early on. Give me a sec. Always make this mistake. What is it called again? Ah, well, that's a strange error because Torch definitely has brand like because we used it. Typos. Okay, and finally, for the last part of our lab today, let me just show you what the forward process looks like when we wait 2 letters. Dot reshape. Whereas, okay. Yeah, I'm so sorry. We are almost done. Like this is like the last thing I wanted to show you guys. If this doesn't work, worked. Right. Okay, final part. So for image in noisy images, plt.imshow, reverse transform uh, that image, and then plt.show. Okay. And there you have it. So this is the forward diffusion process. So this is the image, very low resolution image, and then you keep adding noise to it. You see that it's getting progressively more and more destroyed until what's left, there's very little left. If we did this for more steps, you would see even more things. So to show an example of what running it would look like, let me please. Okay, so this is what it would look like if you are running it for like hundreds of iterations, right? You take the original image and then you gradually destroy it completely. And then for recreation, we use a UNet, we train it. Now we use the UNet to train it on that one image 2000 times. So the only thing that this neural network knows is that image of a cougar. That's the only thing that it exists in its entire universe, that image of a cougar. So once we train it, it will take, on my laptop, it took like 6-7 minutes. It's a 2080 with 8 gigs of RAM. So it might take longer. So this is how the trading goes at 0th epoch, the ground truth noise, and this is what it predicts. And you can see that the ground truth noise is somewhat flat, but our model is predicting something like this. So as our model learns the distribution, it comes closer and closer to the truth. So this is what diffusion model does. It learns the distribution. So eventually, after a while, you keep running this over and over again, and you get back to the image of a cougar. That's it. That's the diffusion model. And all these Jupyter notebooks would be made available. So if you want to run it on your own, feel free. There's a UNet, how we are using it on CFAR. You can see that. Yeah, you can see that running it on my laptop, it tries to predict, tries to create planes, cars, birds. Not very well. These are pretty fairly poor. But if you like squint your eyes and look at it from far enough. Eldritch birds. But yeah, so that's it for diffusion models for today for your class. If you have any questions, I'll share the presentation, the notebooks, etc. on Teams and online. So if you have questions, ask me. Your assignment due date has been postponed, so that should be able to help you as well. So until then, we're okay. We're like 5 minutes over where I thought I'd be finishing. So till then, thank you.